Hi, everybody. Here is another video solution as requested on the forums. This is section 5.2, exercise 13. There's quite a bit of text here, so let's try to read it all together. Let A be an n by n matrix over a field F. Then it says recall from a previous exercise, exercise 14 of the previous section 5.1, that A and A transpose have the same characteristic polynomial, and hence share the same eigenvalues, that should say values, with the same multiplicities. So that's a given. That's something that we're supposed to know from a previous exercise, although perhaps we can someday talk about those solutions as well, or you can work on that exercise on your own. For any eigenvalue lambda of A and A transpose, since they share eigenvalues, let E sub lambda and E prime sub lambda denote the corresponding eigenspaces for A and A transpose respectively. So E lambda is the eigenspace for A with eigenvalue lambda, and then E prime sub lambda is the eigenspace for A transpose with that same eigenvalue lambda. So part A says, show by way of example that for a given common eigenvalue, these two eigenspaces need not be the same. Part B says, prove that for any eigenvalue lambda, the dimension of the dimensions of the two eigenspaces are the same. And C says to prove that if A is diagonalizable, then A transpose is also diagonalizable. So let's start with A. We want to show by way of example that for a given common eigenvalue, the two eigenspaces need not be the same. So let's work really concretely here. Let's pick some A. Let's say we want to make it a 2 by 2 matrix. Let's work over the real field. So F will be real numbers. And we need A and A transpose to be different matrices. So we need to choose something that's not symmetric across the diagonal. So let's just try something really simple, like, I don't know, 1, 1, 0, 1. Let's see, does that have eigenvalues? I guess we can do the normal thing. We can say the characteristic polynomial of this, that's the determinant of A minus T times the identity. So I guess that's just going to be the determinant of 1 minus T, 1, 0, 1 minus T. All right, that's a characteristic polynomial that splits. That's 1 minus T quantity squared. So that will have an eigenvalue of 1, and the multiplicity is 2. So let's see if we can work out what some of the eigenvectors might be. What's the null space of A minus, well, just 1 times the identity? That'll be, if I take that matrix and just subtract 1s from the diagonal, that'll leave us with the matrix 0, 1, 0, 0. And, well, let's see, that says that the second coordinate should always be 0, but the first coordinate can be anything that it wants to be. So T can be any real number, but the second coordinate has to be 0. That's pretty cool because we can see pretty quickly, I think, that A transpose, well, that's just taking this matrix 1, 1, 0, 1 and exchanging the rows for the columns. So now instead of the first row being 1, 1, the first column will be 1, 1. The second column will come from the second row of A, so it'll be 0, 1. And now, right, we can see that, yes, in fact, as exercise 14 suggested, that should have the same characteristic polynomial, 1 minus T times 1 minus T. But now the eigenvectors will be the null space of A minus that same identity. Sorry, A transpose minus that same identity. So that will be the null space of 0, 0, 1, 0. And we can see pretty quickly that that has the condition that the first coordinate has to be 0, and the second coordinate can be anything that it wants to be. So now even much more concretely, we can observe that, for instance, 1, 0, 0 is an eigenvector of A, but presumably it will not be an eigenvalue an eigenvector of A transpose. So let's really check this, that A times 1, 0, well, that's 1, 1, 0, 1 times 1, 0. That'll be 1 plus 1, or 1 plus 0 is 1, and 0 plus 0, 0. Yep, that is in fact 1 times the vector we started with, 1, 0. But what is A transpose times 1, 0? Well, now that's going to be the matrix 1, 0, 1, 1 times this vector 1, 0. And let's see, 1 plus 0, that's 1. And 1 plus 0, that's also 1. So this is not equal to any lambda times 1, 0. Particularly, it's not equal to the eigenvalue 1 times 1, 0. So great, just by sort of trying out a relatively simple example 2 by 2 matrix, we can show part A that for a given common eigenvalue, the eigenspaces need not be the same. There are vectors that are in the eigenspace E lambda that are not in the eigenspace E prime lambda. And probably this works vice versa as well. You could show that the vectors here, so for instance, 0, 1 would be an eigenvector for AT, but not be an eigenvector for A. Great, let's look at part B then. Part B wants us to prove that for any eigenvalue lambda, the dimension of E lambda is equal to the dimension of E prime lambda. All right, so we'll figure out what that really says. What is E prime lambda? Well, that's the null space of this A transpose matrix minus lambda times the identity. All right, it's a set of vectors so that when you multiply them by A transpose, you just get the same as lambda times the identity applied to that vector. So if you subtract A transpose times the vector minus lambda I times the vector, you get 0. So you get a vector that's in the null space of this matrix right there. So let's observe something really quickly. What we'd like to do is somehow relate this to the null space of the appropriate matrix for the original eigenspace, the eigenspace associated to A, this E lambda. So the problem is that there's a transpose there and there's not a transpose on the right, but I guess the transpose of the identity is just the identity. So I could write this as lambda times the identity transpose. In fact, scaling doesn't change that. So why don't I just put parentheses here and make that a transpose? And that's great because the difference of transposes is the transpose of the difference. So this is actually A minus lambda times the identity, all transposed. So this is almost now like the eigenspace E lambda, except for that one transpose right there. So now the question is, given some matrix, how is the null space of the matrix and the null space of the matrix transpose related? So let's observe on the side here. For any n by n matrix, I'll use a new letter, I'll call it M for now. What is the null space of M compared to the null space of M transpose? Well, if you play around with a couple of 2 by 2 examples, you'll see pretty quickly that they're not the same. The null space of M does not have to be the same as the null space of M transpose, but the dimensions of these two null spaces will have to be the same because, maybe less controversially, we know that the rank of M will be the same as the rank of M transpose, because one way of calculating the rank of a matrix is by performing elementary row operations until you get something in reduced row echelon form, and then counting the number of pivot ones. And the number of pivot ones when you do this to M will be the same as the number of pivot ones when you do this to M transpose. So the ranks of these two matrices will be the same. So by the rank nullity theorem, or as we've been calling it in this class, the dimension theorem. Well, if the ranks are the same and, well, they're both n by n matrices, then n is supposed to equal the nullity of M plus the rank of M, but it's also supposed to equal the nullity of M transpose plus the rank of M transpose. And so if the ranks are both equal and the sums both equal n, then the nullity of M must equal the nullity of M prime, and that's exactly the dimension of these null spaces. So that's true for any matrix M and its transpose. So let's go back to our problem. Now, we've related the eigenspace E prime lambda to the null space of A minus lambda i's transpose. So if we take this thing here, this A minus lambda I as our general matrix M, then what we can really say is not necessarily that the null spaces are the same, but that the dimension of E prime lambda, well, that's equal to the dimension of A minus lambda I all transposed, the dimension of the null space of A minus lambda times the identity all transposed. And by our previous discussion then, this is the same as the dimension of the null space of this matrix without that transpose. But then we can recognize that this, of course, is just the dimension of E sub lambda, the null space of the eigenspace of A with respect to that eigenvalue lambda. So that proves part B, that the dimensions of the eigenspaces are the same, even though the eigenspaces are not necessarily the same, as we showed in part A. So finally, part C is fairly straightforward. Part C wants us to prove that if A is diagonalizable, then A transpose is also diagonalizable. And this is just going to be a direct application of theorem 5.9. A is diagonalizable if and only if the characteristic polynomial splits and for each eigenvalue lambda, the dimension of E sub lambda equals the multiplicity of lambda in that characteristic polynomial f of t. So I won't write this down very formally, but let's just see how this would change when we're talking about the transpose. Well, a transpose is diagonalizable if and only if the characteristic polynomial of A transpose. Well, the characteristic polynomial of A and the characteristic polynomial of A transpose are exactly the same, as we're told is true from exercise 14 of the previous section. So this characteristic polynomial splits if and only if the one for A did. They will have the same eigenvalues, and those eigenvalues will have the same multiplicities in the same characteristic polynomial. So then each eigenvalue we'll have to have the dimension of the eigenspace matching that multiplicities, but we just showed that the dimensions of the eigenspaces for A match the dimensions of the eigenspaces for A transpose. So if A is diagonalizable, then these criteria must be met, and then these criteria will be met for A transpose as well. So then A transpose will be diagonalizable. Great, hopefully that is helpful. And again, and as always, I am happy to answer any questions that you guys have. I will see you later.